name is Charles Willis-Dixon. I'm the owner of EcoStructural Products. Our company is involved with heavy timber structures and mezzanine floors in timber. We have been involved in this for the last 28 years, and we have developed a range of timber I-beams that is unique in Africa. For this range of I-beams, we have developed our own engineering policy, and we have done testing with SABS and University of Pretoria in the past. We can develop our own engineering from the results that we receive from the tests. We have a safe load table in our manual, which has recently been published, and the engineers and even architects can actually obtain correct sizes for various spans and load cases from the information in this manual. Our engineering service extends to architects and engineers in terms of preliminary designs, and we were quite happy to produce preliminary drawings which support our proposals for various types of structures. We find this is important as that the interpretation of what we do is clear and concise, and that the recipient professional understands exactly what we are proposing. We then go on to do full working drawings for the installation of the structure once the project has been awarded. Yeah, the timber I-joists in South Africa started 28 years ago in Port Elizabeth, where I was invited by the Institute of Architects to go and deliver a presentation on the use and design of timber laminated beams. And the upshot of this conversation was that the architects were not very happy with the laminated beams. They were heavy and difficult to use, and people didn't know how to design them properly. So they asked me to come up with an alternative, which I did. And we then got the timber I-joist. The timber I-joist is lighter, and in many respects it's stronger, and certainly infinitely cheaper than laminated beams on a span-for-span, load-for-load basis. We then developed the I-beam over a number of years, and we have today developed it so we don't have any loose flanges on the side. We actually have a horizontal flange, as can be seen in this example here. The flanges now have a slot, as opposed to the flanges being laminated on either side of the plywood. And we use high grade S7 flanges, and we use exterior ply in the webs, 12mm thick, and we have a proprietary formula for the slot, which we adopted some 15 years ago. The beams can be manufactured in lengths up to 13.5 meters, and our maximum span capability for a domestic floor is 13 meters. Typical applications for the I-joist are floors, domestic floors, mezzanine floors, ridge beams and rafters in ridge beam and rafter type construction for roofs, lean-to roofs, and girder members in timber structures. The beauty of the timber I-beam is that it can be quite heavily loaded. We have instances in the past where we've worked on key projects, for argument's sake, Planet Fitness. We did a floor for Planet Fitness in Durbanville, and this floor was a span of 7.5 meters and carried a full load of 6.5 kilonewtons a square meter. The floor went up in 3 weeks with only 4 labourers, and there was 21,000 chipboard screws inserted into this floor and 400 bolts. And the result of this floor was a very sturdy structure altogether. In terms of roofs, the I-beams are ideal for sheeted roofs, particularly, where spans of up to 12.5 meters can be achieved, and centres up to 2.4 meters, providing one, of course, has the right purlins to achieve that. In terms of flat roofs, we are one of the only 3 companies in the world that manufacture tapered I-beams. The tapered I-beams has a pitch of 1.5 degrees, enough to roll off 70 millimeters of stormwater at any given point. We have a proprietary drainage channel that is put into the lower end of the beam by the parapet containing the outlets, and providing the beams are inserted or installed perfectly level, then we can run this for up to 30 meters without a drainage point. The whole system works on surface tension at the outlet and is highly efficient. The beauty of this is that there is no wet work that goes into this structure, and the waterproofing is applied directly on top of a shutter ply deck that is screwed to the top of the I-beam. The beauty of that in turn is that the shutter ply doesn't expand or contract. It is inert to movement. Means that the waterproofing membrane of whatever sort it might be is actually stable on top and doesn't shear off under movement from the substrate. That means that your maintenance on that particular roof deck is minimal. Another key project that was accomplished in about 10 years ago was a job we did for Tendrina Power Station, where they had a floor in the central power generating room which could not be accessed by concrete or steel. We did some timber I-joists for this floor. The span was 8 meters. The load was 8.5 kilonewtons a square meter, and we achieved this quite easily. On this particular occasion, we had a bending problem, so we overcame this by adding an additional flange to the bottom of the beam, which drops the neutral axis on the beam and takes the bending out of the whole structure. The secret to the additional member is that it must be in one piece along the continuous length of the beam. Another ideal application for the timber I-joist is in the as floor members for attic frames. In this day and age where construction and alterations to housing is so expensive, there's always people looking around for a cheaper alternative to conventional, being concrete, steel and the like. And we have developed a long I-joist that we call a bridging member, and it literally bridges from one side of the house to the other. This is designed specifically so that other members can be attached to it and a floor laid on top of it to form the floor of an attic frame. We have various options to accomplish this, and in terms of designs in the roof, we have in years gone by accomplished a 8-meter span using diaphragm technology on the floor to provide an attic studio for one client. The walls were taken up 2.4 meters and there was a vaulted roof on top of this structure. We achieved the vaulted roof by way of putting in laminated timber portal frames at 3.5 meter centers with ridge beam type construction and I-joist rafters off either side. We connected that to diaphragm technology in the walls, and the walls were then coated on the outside with a special coating. The floor was a full span of 8 meters, and the diaphragm technology enabled us to retain the stiffness in the floor, which prevented us from having to take out the ceiling underneath. We saved the client a lot of money. Another capability we have is to provide a design and manufacture facility for curved I-joists. This, we understand, is quite unique worldwide. It is not easy to manufacture, it is not easy to design, but it can be done. As in there are curved laminated beams, there can also be curved I-joists. These can be achieved in spans up to 30 meters at up to 4.5 meter centers, and this has been designed already. Unfortunately, the particular project got shelved, so we weren't able to build it, but we have the capability to do this, and we have got inquiries coming in for this facility and for this service. Another application for the timber I-joist is to be used as girders holding up timber roof trusses and or timber rafters, especially in cases where there are long spans. And I'm talking spans up to 6 meters, 6.5 meters in the orifice. The beauty of the timber I-joist is that the deflection on it is far less than that of a laminated beam if it's designed correctly. This means that it does not trap sliding doors or break glass in sliding doors over long spans. And we have the facility within the depth requirement to remove the deflection. Normally we would design our floors for a deflection criteria of span over 250, but for cases of large openings we would design for span over 320. This enables us to put in a cheaper member. It may not be as aesthetically pleasing, but it is certainly a cheaper member than a laminated beam and certainly cheaper than a steel beam. In terms of engineering design, we adopt policy as laid down in SANS codes 10160, 10163 and various associated documents for timber structures. Although we are busy developing our own range of I-beams, new I-beams, we are going to adopt our own strategy for stress grading. This will be based on SANS 10160 and 10163, and we will develop it to the degree where it becomes internationally acceptable in terms of ISO and the Eurocode. Currently, we are using working stress designs, and we will be developing with the new range onto limit states designs. We have codes of practice, right, which is laid down by SANS. So you design a laminated beam, they tell you the loading. The loading code applies to concrete, steel, timber, whatever. Right, that's the one side of it. That's the 10160. The timber code, the 10163, is the timber code. You take that adopted loads out of there and you put them into the other code.
Yeah.
All right. And it's fairly simple once you know how to do it. It's fairly simple and straightforward. That's your code, and that's the standard by which we abide. But now we're going to have to change because of the ISO issue and because we're becoming international. We've now got to start designing in this new thing they call limit states. And limit states is where you don't design moments and what have you directly. You have to go through stating the limit of the capacity for the beam, and you work back from that. But I've been listening to our engineer, and he's having a fit on this stuff because it refers to, you go and you get one piece of information out of one code, and it refers to a chapter in another code, which refers to a chapter in another code, and a chapter in another code. To do a simple design, you're going to be there for like 2.5 hours. I mean, it's ridiculous. And there's only one real type of software that you can use to circumnavigate that, and that is Procon. And Procon clocks in at $45,000 for the package. The single frame analysis package is $29,000 now, all right? And you need to be a rocket scientist to drive this. So we're looking for something simple, and that's where that page in the manual comes from. We have that little bit of a software that Richard's developing, and it just works off Excel. I mean, it's nothing, no rocket science, yeah? We once had an inquiry, we put an inquiry out at University of Pretoria for their computer programming faculty to actually write some software for us that we'll get it cheap, you know. They wanted 6 months to do it, and they wanted $41,000. And that was in 1996. And it is, because that's like, could be, we've just done one now for a guy, Anglo-American. He wanted a roof garden on his new house, okay? So he's an architect, and whether he's got his load screwed up or what, I don't really know. But we finished up with a total load of like 3.5 kilonewtons a square meter on this roof. And he had spans of like nearly 6 meters. We had a beam 444 deep just to span that, with all his decking and his soil and his grass and his plants and whatever. And this is another like nearly 200,000 rands worth of work. It took me 15 hours to sort this out. You know? And it's not, we've got to find some way of circumnavigating that, and I'm hoping that that's where it's going to go. The nature of the timber I-beam is such that it is very good in terms of strength to weight ratio. This means that in developing projects in Africa, that the use of the I-beam is ideal in terms of roofs and floors because of its lightweight nature and the ability for it to be packed easily into containers. This means that industrial structures in Africa can be well and truly be achieved by adopting the use of timber I-joists or timber I-beams, coupled with laminated beams if necessary, and even mixed with certain steel components for major supports. The fact that the beam is so light reduces the logistics costs quite considerably, and the logistics are even further reduced by the fact that we can pack a lot more I-joists into a container than you would normally be able to do with laminated beams, given the lightweight nature of it. And once we have produced installation drawings for any given structure, we then wait for the contractor to install the structure, and we follow up then with our own inspections. Whether we do the inspections ourselves or we appoint independent engineers to do the inspection is neither here nor there. The inspection must be done. Following which, upon successful completion of the structure, then we will certify the structure through our own engineers. Then the structure, having been certified, will be certified to the approved loads that were given in the first instance. This is the load span. Right? So for argument's sake, you've got a domestic floor. These are all domestic loads. Domestic floor, and you've got a span of, say your floor is 5.3 meters. You need an ES3P. And an ES3P looks like that. So if you're an architect, you know immediately what you're in for in height constraints and all that kind of thing. And they all go in, the design criteria is all laid out in here. And the centers of the floor just 488 millimeters. And that's it. That is what came out of all the testing. And we designed specifically for moments and shear. Okay? And the EI is for the deflections. We've got some quite serious deflection criteria in there. It's really nifty stuff. Now, I have a program where I can play with these sizes, okay, and different grades, which enables me to come up with hybrid beams.
Oh.
Yeah, and that's so to that extent we have got this facility to change things around a bit, but it only helps in terms of getting the information out of the architect's drawings and determining the loads and calculating the loads and working it out all by longhand, and then going to this and saying, okay, fine, we've got that amount of load, what size beam do I need? And that comes out there. And if it's wrong, or we can't get it in, or we can't fit it in, then we start playing around on the computer and changing things to make it work. Timber I-joists being made from a natural resource, being timber fibre, are ideal in terms of eco-building. They're sustainable, they are made from a renewable product, and in terms of common building practice nowadays, they certainly have a very low carbon footprint. In the most part, the structures that we design are at least 90 to 95% timber. We don't use steel unless we absolutely have to, other than for connectors and fasteners. This means that our structures are very eco-friendly, and as mentioned previously, we are only using timber from FSC forests. Okay, the timber that we use coming from FSC forests, and only high-grade material that we use, can be replaced quite easily from the right sector. We here in South Africa and the Southern Cape region have some of the best structural timber in the world, and the problem with it is that it is not exploited to its full extent. We need to be in a position where we have specifiers who are involved with green technology, specifying structures that contain the likes of timber I-joists and high-grade laminated beams in order to take full benefit of this resource. There are companies that we know of in terms of timber roof trusses who are importing timber from South America, but this is totally unnecessary, because if they did actually start to select out the right kind of timber for these structures, then they would be able to use the local resource and hopefully at a cheaper price. In terms of qualifying the manufacturing of our beams, we use SATAS, that's the South African Timber Auditing Services, as quality control unit. We have our own 1/3 dead load testing machine on our shop floor, and we take batches of beams every now and again and test them under the supervision of SATAS. The SATAS mark is quite important to us, and we have recently developed a new range of beams which is now being tested and will be marked in due course. We will have a look at this testing machine. It is not very sophisticated, but it is highly effective, and it is very important that beams are tested to their ultimate limit in certain batches. Acknowledged authority on timber structures, so I was very lucky to have him on board. That's why this has come so far forward. And he got hold of their results. Then we went downstairs to the lab, we ordered another load of beams from Mondi, and we took them into his own test. Then we started getting some results. And he even went down to Stellenbosch, to the university in Stellenbosch, right, where they got an enormous testing facility there. And they got a bank of computers, it's as high as this room. They can plug these beams in. We wrecked a mountain of beams. There must have been 200,000 rands worth of beams we wrecked to get the right results. Wow. So we can't say this hasn't been tested and we don't know what we're doing, because the results were all there. In summary, timber I-joists are a significant advantage in design of heavy structures as opposed to steel. It does have its limitations, and it only works in certain circumstances where the loadings are appropriate for the use of this kind of product. But it doesn't alter the fact that up to certain spans, that the timber I-joist is stronger, lighter and cheaper certainly than laminated beams, and is certainly lighter and in some cases equally as strong and cost effective as steel. This needs to be put to the test to a further degree in terms of having the ability and the opportunity to design structures for professional engineers and architects.